Let's talk about what I have found to be students' top 5 limit mistakes in calculus. Number 1, thinking 0 over 0 always means the limit does not exist. If we have a limit where we apply direct substitution like this one, and we end up with 0 over 0, I like to tell students, oh no, that means we need to do more work. And usually that work is algebra. So here, what we would need to do is factor and cancel to remove the discontinuity and then substitute in the value, and you will find that the limit does in fact exist. The next one is bad algebra. So when we have a limit of a rational expression, we have to try to factor and cancel. We cannot simply cancel terms. So too many students are going to try to cancel these x squareds. Here, when I have a square root involved, students' mind goes to squaring things. Well, I can't just randomly square the square root or square the numerator. Here, we want to multiply the numerator and denominator by the conjugate of the numerator. Number 3, mixing up the type of limit. The limit as x approaches a number of f of x and the limit as x approaches infinity of f of x are asking for two different things. This first one we've looked at already. Here we're looking at the limit as x approaches the number 2. We'd have to factor and cancel, and that's going to give us the y value of a hole in the graph. Here, if we're looking at that same function, the limit as x approaches infinity is looking for the end behavior of that function. So here we're looking for the horizontal asymptote of this rational function. So we have to look at what the limit is approaching to determine what strategy we're going to use. Number 4, graphical limits, thinking that a hole in the graph means the limit does not exist. So here, the limit as x approaches 1 of f of x is in fact equal to 1. So from both sides, from the left side of 1 and the right side of 1, I'm approaching this y value 1. So the limit does exist. It doesn't matter that there is a hole in the graph there. Similarly, at x equals 4, the limit as x approaches 4 from the left and the limit as x approaches 4 from the right, those are both getting closer to 1. So the limit there is 1. Don't be fooled by the point up here. That doesn't matter. Limits only care about what y value we're getting close to. It doesn't have to be defined there, like at 1, and it can be defined somewhere else. And finally, one-sided limits confusion. So sometimes when students see a limit from one side, they automatically think they need to plug in a number on that side of the value. So here, plug in 3.9. Well, that wouldn't be a terrible idea for this one, but that's because when you do direct substitution, you get 1 over 0, so there is a vertical asymptote there, and we are looking for whether the answer is positive infinity or negative infinity. We're looking for the behavior on the left side of 4 near the asymptote. But that's not the case for the second example. So here, even though I'm approaching 4 from the left, it turns out this two-sided limit exists. So just because we see from the left doesn't mean we're going to do something like plug in 3.9. We would actually substitute in 4, see that we get 0 over 0, indeterminate. Oh no, we have to do more work. We would factor and cancel, and we would see that we actually get out a value of 8. And so if the two-sided limit is 8, then the one-sided limit is 8. So we do not always have to substitute in a value on the left side or the right side if we're doing a one-sided limit. It depends on what happens after you apply direct substitution. So a non-zero number over 0 means there is a vertical asymptote. So our analysis is going to be different than if direct substitution leads to 0 over 0. What we do from then on is going to differ. If you want some more in-depth examples of all of these types of problems, go ahead and check out my full-length videos.